Alrighty guys, we are going to start our brand new chapter all about similar triangles and similarity. We're going to start off with just similarity in general and then move more towards just triangles. So still in triangle land, just dealing less with like crazy points of congruency and stuff. So on our table of contents page, the first thing that we're going to talk about are ratios and proportions, which I always struggle to spell, proportions, and I wrote on top of it. That is going to be on page 63 and 64. And I think ratios and proportions are kind of easy, but they are a big deal when it comes to similarity. We talked about similarity briefly before, so here's 63 and 64 when we were talking about congruent triangles. So triangles are congruent if they are identical. All the angles are the same and all the sides are the same. What we're going to find out is that similar stuff has some things that are identical, but most things are related by a certain factor. And that's why like a factor or a multiple of something might be a nice easy number like 2, but sometimes it's not a super nice number. And that's why ratios are going to be super important in this chapter. So let's get to it. Now, if you're taking notes with me live in class, then this video is irrelevant, but if you missed it for any reason, you're going to want to watch and take notes. So firstly, we have what is a ratio? Ratio is actually, the word itself is just like a lazy way of saying rational. And because the word's right in it, like ratio, rational. A rational number is just a fractional number. And it could be a whole number because, a fractional number might be 1 over 2, or it could be 2 over 1, which is really just 2. So I can always make a whole number, fractional number, by throwing it over 1. But a ratio, just a fraction. So a ratio is a relationship of 2 or more numbers or quantities. Can be written a couple of different ways. The way that I prefer is as a fraction, so like A over B. But a way that you may have seen before is where we use like a colon, so A dot dot B. Or if you're just going to write it out in words, sometimes we just say A to B with the word 2 in between. But no matter what, like first number is always on top, or first is first, and then the second number is on bottom if we're thinking fraction land. We should always, 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 because we are talking fractions here, we should always want to be reduced. So it must be reduced, if possible. So a quick little example, the football team played 62 regular season games last year. If they won 34 games, what is the ratio of wins to losses? So they're telling me right there what needs to go first and what needs to go second. Wins need to come first, and we won 34 games. Losses, well, they didn't tell me outright, but I can pretty easily find it because we played 62 games. So if I do 62 minus 34, we'll get 28. So to 28 losses. Now, I would prefer it as a fraction, so we would have 34 over 28. And then I do need to reduce, and I can reduce because they are both at least even, so I can divide by 2, and we'll have 17 over 14. And then I noticed I can't reduce anymore, so that must be it. Ratios of wins to losses is 17 to 14. Easy, easy. Now to extend that a little bit and make it a little bit more tricky, we can talk about an extended ratio. So a typical ratio is just a fraction, one number to one number on top, one number on bottom. But I can do extended ratios for geometry purposes, and that's where I relate more numbers than just 2. Okay, so it's a relationship between 3 or more quantities, or really like greater than 2 quantities. So for 2, it's just a ratio, but an extended ratio is going to be more than 2. So 3, 4, 5, any amount of numbers really that I want, more than 2. And so we wouldn't be able to write that as a fraction anymore, unfortunately. We kind of have to use the dotties. So like A to B to C to whatever, like D, E, F, G. Now, again, that's really important for us, like in geometry, because we can use it for problems like this. So the ratio of the measures of the 3 angles in a triangle is 3 to 7 to 10. Find the measure of the largest angle. Well, so if 3 is referring to one of the angles and 7 is referring to another and 10 is referring to the last, I know that this angle here is the largest one because it's like the 10, like that's the biggest number. The sneaky thing is, so if we think about this like as a triangle, if I kind of draw one out, it could be that one angle measures 3 degrees and another angle measures 7 degrees and the last angle measures 10 degrees. And my picture is really bad, so stop judging me. But that's probably not accurate, because one thing I know for sure about the angles in a triangle is that they all need to add up to equal 180, and these sure don't. They only add up to 20. So the thing is, because when I write a ratio, I need to be fully reduced. There's potentially a number that I divided out of all of these. Kind of like up here, I was able to reduce by 2. The thing is, I don't know what I reduced by, so I just need to call that thing x, since it's something that I don't know. And when I reduced by it, I divided it out. So to get it back, I need to do the opposite of that and multiply it back in. So all that to say, like if they give you an extended ratio in a problem, chances are you're going to want to put an x behind each of the numbers in the ratio. So 3x, 7x, and 10x. And then you're going to want to do something with those numbers to figure out what that common multiple was that I divided out. Now in this case, because we're talking about the measures of an angle, I know that in a triangle, the measures of an angle will always add up to equal 180. So that's a thing I can do with these angles to help me solve for x. You might see that they tell you instead something about the sides. And if they do, then they'd have to give you something like the perimeter, because then I could add them all up and set them equal to the perimeter. Or maybe they could tell you about the area, because we have an area formula for that. So it just depends on the context of the problem. So for this one, again, because we're talking about the measures of the angles, I know that they'll always add up to 180. And I can do that because now these are all like terms, and we'll have 20x equals 180. And I can solve for x by dividing the 20 both sides and get that common multiple that was divided out of each one. So zeros divide out, and we're left with 9 was divided out of each one. And then I could go back and find the measure of each of the angles, but really I just need the largest, which again is the one related to the 10, which would be 90 degrees. Oh my God, this was a good picture. I just put the numbers in the wrong spot. So largest angle equals 90 degrees because we did 10 times 9, which was x. Oh my gosh, my notes are a mess today. I don't know what's wrong with me. Okay, last but not least, proportions. So a proportion is just where I take 2 ratios and say, y'all are equal, which hopefully, like, it's obvious that they're equal, but if not, then I might have to solve for some things. So a proportion, my desk is a mess, I'm so sorry, is an equation, so equal sign, that states 2 ratios are equal. I mean, yeah, duh. A proportion you're always going to want to write as 2 fractions equal to each other. If you write the ratio with like the dotties in between, and then the equal sign in between, we don't have a way to solve that. So you're definitely going to want to write it as a fraction, so a ratio fraction, is going to be equal to another fractional ratio thing. So like C over D. And there's lots of different ways to solve two fractions equal to each other, but kind of the best way or the most straightforward way is to do cross multiply. And when we do that, what happens is I end up doing A times D, and that will be equal to C times B. And that's helpful for solving purposes because like I might just get my answer at that point, or I might need to do one more step to find my answer. So a good example of using ratios to, or using proportions to solve rather, use the given ratios to solve each problem. If these two ratios are equal to each other, and again, I'd have to be like told that they are because I can't see like obviously they are. But since it's shown that they're equal, we can solve for x by cross multiplying. So I just have to be careful here because when I'm going to do 10 times this number, I have to fully times the 10, so kind of like distribute. So 10 times all x minus 9. And then same thing going the other way, 15 times all of the 2x minus 9. So that just means we're going to want to distribute. So you can see like after I cross multiply, there's still some steps for me to do. So we'll have 10x minus 90 and then 30x minus 135. And then if I'm going to want to solve for x, I'm going to move the smaller one. So I'll subtract the 10x. And since it'll be over here, I'll add the 135 away. And so then once we simplify, we'll have 45 equals 20x. And then one last thing to solve for x, we'll divide by 20, which won't fully go, but I can reduce at least by 5. So like 5 will go into 45 9 times and into 20 4 times. And then I can see I can't reduce anymore after that, and I'm probably just going to leave it as a fraction because this is ratio land, my favorite land, fraction land. Alrighty. Let's stop this one there. I know we have the other page, but I'm going to do that in a separate video.